Okay, so let's start this session. So first of all, good evening everyone. My name is Devlina Maiti. I'm a research scholar in the Department of Mathematics, IIT Kharagpur, and also I am an NPTEL TA for this course Real Analysis 2, and this is the first tutorial. And okay, I think no one will join from here, so we'll start this session. So we'll start with the basic definitions like metric space, norm space. Fine. So first, we start with the definition of metric space. Right? So suppose X is a non-empty set. Right? And we say this metric space xt, this is a pair where X is this non-empty set and D is distance. And distance between the points of X. Right? So D is a mapping from X cross X to R. So it is a metric. So we say xt is a metric space if it satisfies some conditions. So the first condition is, so here this dxy, here we take a tuple which goes to dxy, which is real. So the metric space, if it satisfies, the first condition is that dxy has to be non-negative, right? Because distance is always 0 or positive. And second condition is the distance is 0 if and only if x equals to y, right? And the third one is the commutative. It is, so dxy and dyx both are same. And the last condition is triangular inequality, which is xz less equals to dxy plus dyz, where this x, y, z belongs to x. So xt will be called a metric space if it satisfies these properties, these conditions, right? Now we see some examples. So the first examples, which is on the real line R is the real line, and suppose D is the metric and D is defined by this mod x minus y. So this is trivially the Euclidean distance that we name it Euclidean distance between 2 points in R. So it is metric because it satisfies all these properties, right? So you can check these properties, this is trivial. And similarly in R2 we can define the Euclidean distance. Since the point is in R2, this xy belongs to R2, means x equals to some x1 y1 and y equals to some, x equals to let x2 y x1 x2, and this is y1 y2. So dxy is root over x1 minus y1 square plus x2 minus y2 square, right? This is a Euclidean distance in R2. And similarly in Rn, the n dimensional, we can define the distance, the metric, by this x1 minus to xn minus yn square. right? So all this D, this D and this D satisfies these properties. That's why R with this this metric forms a metric space, right? Now let's this is first example. Let's go to the second example. So the second example is CAB, which is a function space. So CAB is nothing but the collection of all the functions f, which is a mapping from this AB closed interval AB to R, and it is continuous. This C is for continuity. Okay. So CAB is the class of all functions defined in closed AB, and it is continuous, right? So you can define a metric in this function space, because each point here is a function, not a point. Each point here is a function element. So if we define this metric, so this metric between 2 points means 2 function. So DFG is defined by supremum of ft minus gt, where t belongs to AB, this closed interval AB. Okay, so this defines a metric in this CAB. So this means this D satisfies all these properties, right? So the first M1 is trivially satisfied. This is greater or equals to 0 because there is a mod, right? And second one, for the second one, dxy is 0 if and only if x equals to y. If f and g are equal, then dfg is 0, right? But for the converse part, f equals to g implies dfg is 0, right? Now suppose dfg is 0. Means what? This means supremum of ft minus gt is 0, right? Now this value is positive, modulus of something is always greater or equals to 0, and supremum for each t, the supremum value is 0. This means for every t it is 0, right? So this implies ft minus gt equals to 0 for all t belongs to AB, right? So this means f t equals to gt for all t in AB, and this implies f equals to g, right? So second one is also true for this metric, and it satisfies the commutativity property. And for the triangular inequality, it is easy to show, because modulus of a minus b is less equals to modulus of a plus modulus of b, and like this you can show that this also satisfies the triangular inequality property, right? So CAB with this metric forms a metric space, right? Now let's take another example, which is the discrete metric. So for discrete metric, let x be any set, and we are defining the distance d from x cross x to r by dxy equals to 0 if x equals to y, and 1 if x not equals to y. So the distance takes only two values, 0 and 1, right? So this dxy is a metric. This d satisfies all the properties. So this D, this is called the district metric in X. Right? Now we'll see some problems. So the first one is, so let D be a metric on X. Now we have to determine all constants K such that this KD and D plus K is a metric on X. Right. So D is a metric and we have to find all those K for which this KD is a metric and D plus K is a metric. So this is very easy from the definition of metric. So you can answer if you can do this. So are you trying this or? So for the first one, when is KD is a metric? This means KD has to satisfy all the properties, this M1, M2, M3 and M4. So what is the value of K for the first one? Anyone? Just use the properties. Okay, so this means this KD has to satisfy all the properties. So the first property was what? That it has to be non-negative, right? So KD, this means if we take D1 to be K into D, then this D1 of XY has to be greater or equals to 0, right? So this means K of dxy is greater or equals to 0, and we know that dxy is always greater or equals to 0. D is a metric. So this implies K is always greater or equals to 0. Right? So for first one, if K is greater or equals to 0, then it will be a metric. And see, all the properties will be satisfied. Because KD also satisfies commutativity property and it is 0 only when xy is 0, x equal to y, right? So for the first one, if K greater or equals to 0, then 1 is a metric. And what about the second one? Please try, everyone. So when is D plus K is a metric? Shraddha?
Yes, ma'am.
Can you answer this one?
Uh, K equals to 0.
Yes. So, yes, you are right. So D plus K is a metric means the first property, if D1 is this, then D1 has to be greater or equals to 0. This property satisfies, and dxy equals to 0 if and only if x equals to y, right? So d1 xy is 0 if and only if x equals to y. This means dxy plus k is 0 if x equals to y, and since d is a metric, so dxy is 0, so k equals to 0, right? As dxy equals to 0. So if k equals to 0, then d plus k is a metric, right? Okay, let's go to the next problem then. So first one is so if dxy equals to x minus y whole square in R, then does this define a metric? So we'll see that this first one is not a metric. So if we choose, for the first one, if we choose x equals to 0, y equals to 1 and z equals to 2, then we'll see that this dxz, which is equal to 2 square, dxy will be 1 and dyz will be also 1, right? So dxz is not less than dxy plus dyz, right? So this is not true, so it does not satisfy the triangular inequality property, so that's why it is not a metric. So what about the second one? Is it a metric or not? If you can do this, you can answer. Okay, so Amandeep, Are you listening? Okay, so we'll see that this defines a metric on R. So it will satisfy all the properties. So the first property, first and second is easy to see, right? First, second and third. And for triangular inequality, it will also be satisfied. See, so for triangular inequality, we have to show that this dxy less equals to some dxz plus dzy, right? So it means it is mod x minus y less equals to right. This we have to show, and it is true because if we take the square, then it will be what, this mod x minus z. Okay, we already have this one, this mod x minus y is less equals to, right? This is the triangular inequality from modulus, right? So here if we do the squares, then it will be I don't know if this is correct. Okay, let's try this one. So this we have here. So this means modulus of root over is this one, and we can show that this less equals to this means what? This means root over a, we are using this one, root a plus root b, right? This will be true. So using this, we found that this root over mod xy, this means what? This means d of xy is less equals to dxz plus dzy. So it satisfies the triangular inequality property. Okay, so this d, so it is a metric. It's a metric on R. Okay. Okay, now we'll define norm spaces. Okay. So let X be a vector space. I hope you know the definitions of a vector space, right? Vector space means X is a non-empty set with two operations plus and dot. and they satisfy some property according to these two operations, right? So X is a vector space, and this norm we are defining from X to R that satisfies some properties. So the first one is this norm is greater or equals to 0. This is positivity condition. Second one is similar to the metric if and only if X is 0. The third one is norm of alpha X is mod alpha into norm X, where alpha is a scalar. And the fourth one is the triangular inequality property. This is norm of X plus Y is less equals to norm X plus norm Y, right? So if this function norm satisfies these four conditions, then we say that X with this norm is a norm space, right? Okay, now we'll see some examples of norm space. So the examples we have taken in for metric. So the first one was for the Euclidean metric on R, right, which is defined by this norm, this distance, this one. So from norm we can find metric always, right? So this is a note that a norm on X always defines a metric. A norm on X always defines okay, I'm telling the relation. So this norm will define a metric on X. How? Suppose xy belongs to X, then we can define dxy by norm X minus y, right? And we'll see that this dxy will satisfy the properties of metric spaces, that m1, m2, m3 and m4, right? From the properties of norm we can find that this dxy will satisfy the properties of metric. So from a norm we can always find the metric. This metric is called the metric induced from this norm. So this metric will be called the metric induced from the norm, right? Now from a norm we can always find a metric, right? But the converse is not true. If there is a metric, we cannot say that this comes from a norm. Not all the metrics comes from a norm. That we'll see in the examples. So the converse part is not true, right? I'll give an example, but first we will see some examples of norm spaces. Okay. So the first one was what? That is the Euclidean metric, right? So in R we have seen the Euclidean distance, which was this x minus y, right? It was the usual distance on R. Now this distance comes from this norm. If we can define the norm in R by mod x, right? If we define norm to be this mod x, then dxy, the metric induced from this norm is what? This is norm of xy minus y, x minus y, which is nothing but mod x minus y, right? So this norm is the usual norm in R, and similarly in Rn, in Rn, now define this norm. The norm is defined by this norm x. I am defining by, so x belongs to Rn means x has n components. These are n tuples, x1, x2 to xn, right? So norm x is defined by root over mod x1 square plus mod x2 square to mod xn square, right? This is a norm. This will satisfy all the properties, right? This is trivial to check. So this is a norm, and the metric induced from this norm is what? It will be mod will cancel out, so it will be x1 minus y1 square to xn minus yn square. So this is the usual metric on Rn that we have already defined in metric space, right? So that metric is coming from this norm. So this D is the induced metric from this norm, okay? So you have defined these two norms, this norm, this dxy is this, and for dr you have defined this norm, okay? Now also we have in example 2 we have taken this class CAB, right? So can we define a norm here such that the metric we have defined, that is this, the metric we have defined by supremum of xt minus yt, right? T belongs to AB. So can we define a metric such that this metric is induced from that norm? Yes, here we can define the norm. So the norm, suppose if x belongs to CAB, right? This means x is a function, x is a continuous mapping. So the norm of x I am defining by supremum T belongs to AB mod of xt, okay? So if we define this norm, then this dxy will be the metric induced from this norm, okay? You see that's dxy, which is norm of x minus y, and which will be equal to this supremum of mod xt minus yt, right? So in the third example we have taken the district metric, right? So now the question is this district metric is induced from some norm, right? So this is the question now. On suppose a set X, can be induced from a norm defined on X. So what is the answer? So we'll see that this is not an induced metric from a norm, right? Now to see that result, we need some result first. So first we need this result. Which says a metric induced by a norm on a norm space X so if D is a metric which is induced from a norm, then it has to satisfy some property. So the first property is dx plus a y plus a is dxy. So it is translation invariant. And the second property is d of alpha x alpha y equal to mod alpha dxy, right? For all x, y, a belongs to x, and for every scalar alpha, right? So if the metric is induced from a norm, then it satisfies this true property. It has to satisfy, right? First we will prove this result. This is a easy proof. So this D comes from a norm. So for the first one, so the dx plus a y plus a is what? So since it comes from a norm, so it is x plus a minus y plus a, right? Because we have defined this. This is the induced metric. dxy is norm of x minus y, right? And it is nothing but x minus y, and which is equals to dxy, right? So first one is proved, and for the second one, d of alpha x alpha y equals to norm of alpha x minus alpha y, and since alpha is a scalar, so it will be mod alpha of norm x minus y, which is mod alpha dxy, right? So this result is proved. So now if discrete metric is induced from a norm, then this metric D has to satisfy these two conditions, right? So we'll see if this metric satisfies or not. Now for the discrete metric, so it is what discrete metric is. It is 1, 0 if x equals to y, and 1 if x not equals to y, right? So let's take x not equals to y, right? Then the first one will be satisfied, because x equals not equals to y means dxy is 1, and also x not equals to y means x plus a not equals to x minus a, so it will also give 1, right? And take alpha not equals to 1. Alpha is a scalar and alpha is not 1, right? Or we can say that mod alpha is not 1. Take alpha such that modulus of alpha not equals to 1, right? Then what is d alpha x alpha y? Since x not equals to y, alpha x not equals to alpha y, so this implies d of alpha x alpha y is 1, because if x not equals to y, then it is 1. And dxy is also 1, so d alpha x alpha y is not equals to mod alpha of dxy, right? So this implies this t this distinct metric is not induced from a norm. Right? It is clear, right? So if you have any doubt, you can ask. Okay. So now we'll discuss about the open balls and open set. Okay. So what is open ball with respect to a metric? So first, so let xt is a metric space. A metric space, and suppose x naught belongs to x, right? Then the open ball centered at x naught with radius r, that is denoted by this b x naught r. Now we will define it by two ways, with respect to metric and with respect to norm. Okay, so this b d x naught r means the open ball with respect to the metric d is defined by all this x belongs to x such that the distance d x naught x is less than r, right? And similarly, if d is replaced by this norm, this means all the x belongs to x such that norm of x naught minus x is less than r, right? So this is defined as open ball. And what is an open set? Open set means so here the same xt is a metric space, or we can define it in norm space also. Okay, so let u is a subset of x, right? Then u is said to be open in x if for each x in u there exists some Rx greater than 0 such that this Bxrx is contained in this U. So U will be open if with respect to each point there will be some open ball which is completely contained in that open set U. Then it will be called an open set, right? So that is, this means what? This means U is open if and only if each point of U is the center of some open ball contained in U, right? So if U is an open, U is will be called open if for every point, if X is any point in U, then there has to be a open ball around this X. This is Rx with radius Rx, so it is Bxrx, which is completely contained in U. If this happens for each point, then it will be an open set, right? Okay, now we'll look at the open balls in R2 with respect to different metrics, right? Okay, so we'll discuss about open balls in R2. So the first metric is, suppose we are taking D1, where D1 is defined by okay, where this X is x1, x2, and y is y1, y2, and they belongs to R2, right? So the first thing is D1 is a metric in R2, right? D1 is a metric, and we want to see what is the open ball of R2 centered at 0, 0 with respect to the radius 1, right? So open balls, so we are seeing B Z0 R, where Z0 is 0, 0 and R is 1, right? So what is BZ0 R here? So it is collection of all xy in R2 such that this distance between D1 of xy and 0, 0 is less than 1, right? So it is xy belongs to R2 such that D1 of these two means then mod of x plus mod of y is less than 1, right? Because Z0 is 0, is this one, this Z0 is the origin and R is 1, okay? So BZ0 R here is this set. Now what does this set looks like? So this this mod x plus mod y less than 1 means it gives 4 equations, right? So this will give 4 equations. This x plus y less than y, x minus y less than y, minus x plus y less than 1, and minus x minus y which is less than y 1, sorry. So these 4 equations will give this region. This line will be x plus y equals to 1, and the next will be x minus y less than 1, right? So this region is nothing but this region. Okay, this is x and this is y. So this region is what? This is b d1. This is with respect to d1 0 0 1, right? Now we'll take a different metric. So now we'll define d2, right? So d2 is defined by, suppose d2 is the usual Euclidean metric. So d2 is what? So now d2 here is Euclidean metric. This means this is x1 minus y1 square plus x2 minus y2 square, right? This x is x1 x2 and y is y1 y2. Now what is bd2? This 0 0 1. It is what? It is collection of all xy in R2 such that d2 0 0 xy is less than 1, right? All this xy. Now d2 0 0 xy means this is root over x square plus y square is less than 1. Now this equation is what? This is equation of the circle, right? Centered at 0 with radius 1. So this is x square plus y square less than 1. So what is this unit ball then? It will be the circle. Right? This circle. So here this circle is the open unit ball. It is B D2 0 0 1, right? Now we'll define another metric on R2. So the next one is, it is d infinity, which is suppose defined by d infinity xy is maximum of mod x1 minus y1 and x2 minus y2, right? And you will see that this defines a metric. It will be a metric, right? So your exercise is to check if these three are metrics. It will satisfy all the properties, but if we do it by your hand, then it will be easier for you, right? Then you will remember. So this d infinity is a metric, and with respect to this metric, so now d infinity 0 0 1 is what? It is all those xy such that d infinity 0 0 xy, the distance between xy and 0 0 is less than 1. So it is what? It is all those xy such that maximum of So maximum of mod x mod y less than 1, right? Now what does it mean? Maximum of this less than 1 means mod x is less than 1 and mod y is also less than 1, right? So the figure will be what? So if this is xy, then mod x is less than 1 means it will lie between -1 to 1, and mod y is less than 1, then it will also, y will lie between -1 to 1. So it is a square. Right? So it is d, the ball be d infinity 0 0 1. Right? So we have in R2 we have taken 3 metrics and we have seen the unit balls with respect to different metrics, right? Now if I put it in the same figure, then you will see that right. So if we look at the norms induced from this, then the first one I am defining. So suppose I am defining norm of xy in R2. I am defining this norm by mod x plus mod y, right? And the metric induced from this norm is d1, right? This d1. Okay, so this is norm 1 and norm 2 is the Euclidean norm, which is mod x square plus mod y square whole to the power half. And similarly we can define p, norm p, which is mod x to the power p plus mod y to the power p whole to the power 1 by p. And this norm infinity is maximum of mod x mod y, right? So with respect to these norms, these metrics are coming, right? So the first one, this comes from norm, this is norm 1, and this circle is from norm 2, and the square is coming from norm infinity, right? And if we draw norm p, it will lies between this 1 and infinity, right? Norm p lies here, somewhere here, right? It will be norm p, where p is greater than 1, right? P is greater than 1. Now the question is, if p is less than 1, then does it define a norm? So the question is, now suppose choose p is half. Choose p equals to half. So this norm half I am defining by what? It is root over mod x plus root over mod y whole to the power 2, right? The question is if this is a norm. Is it a norm? So you see that this is not a norm. Now if we take these 3 points, suppose x is 0, 0.9, y is 0.9 comma 0 and z is 0, 0, then we will see that this dxy, norm x minus y or x plus y is not less than or equal to norm x plus norm y, right? So it will not be a norm. And if we choose the open ball with respect to this norm, then it will look like this. Will be what? This will be xy such that root over mod x plus root over mod y whole square is less than 1, right? Now this equation will give what? This equation, I'm drawing this here, it will look like this one. Right, this region. Now if you observe this all the norms we have defined from 1 to infinity, all the open unit balls are convex, right? But the open unit ball with respect to this one, this d half, will not be convex, right? So this will not be a norm. This is a metric. D half is a metric, but it does not come from a norm, right? So this is an exercise which says let X be a norm space, right? Then the closed unit ball which is closed unit ball which is all those x such that norm x less equals to 1 is convex, right? If it is a norm space, then the open unit ball has to be convex, right? For this reason, this one is not a norm. So this is not a norm, right? This d half we can define mod root over mod x minus y plus this, but this it is not a, because the open unit ball which is coming here, this set, this is not a convex set, because if you take this 2 point, suppose close to this one and close to here, then the line segment joining these two does not lies completely on this set, right? That's why for all those p which is less than 1, it will not define a norm. For norm, the p will be greater equals to 1, right? So it is clear. So this is exercise. Now let's go to problem 4, I suppose. So suppose xt is a metric space and x naught belongs to x, and where this D is the distinct metric. So it is this discrete metric, right? So what is the open unit ball here? So BD x naught 1 is what? All those x belongs to x such that D x naught x is less than 1, right? And in discrete metric the distance is either 0 or 1. So it is less than 1 means it has to be only x naught, right? So it is only x naught. So the open unit ball with respect to x naught is only x naught. So this means the singleton sets are open. This singleton set x naught is open in X, right? So every singleton in X is open, and if A is a subset of X, then we can write A to be union of all the members of A by this singleton set, right? You can write A like this, and all the singletons are open, and we know that arbitrary union of open set is open. So this means this A is open. So any subset of X is open in discrete matrix, right? So therefore each subset of X of a discrete matrix space of a discrete matrix space is open, right? So since each subset is open, then all the set will also be closed, right? Because this singleton set can be written as x minus a, right? Now this set x minus a is this is a subset. X minus a is a subset of X, and any subset is open, so this is open, right? And since this is open, X minus a open set, it is closed, right? So this singleton set is also closed in X. So any subset in a discrete matrix space is open and also closed, right? Okay, now we'll define the equivalent matrix space. Okay. So equivalent matrix space means two metric D1 and D2 on a non-empty set X are said to be equivalent if the collection of all the open sets that is the topology of the matrix space, right? Because the collection of all the open sets define the topology of the set, right? The collection of all the open set is same open sets of the matrix spaces metric space, suppose xd1 is same as the collection of all the open sets of xd2, right? The collection has to be same, but that does not mean the open balls has to be same, right? We'll see that this in R2 all the metrics I have defined here, this d1 d2 d infinity up to d infinity, all the metrics are equivalent. The open balls are different, but the collection of all the open balls, all the open sets will be same, right? Okay, there is a theorem which says let d1 d2 are two metrics on a non-empty set X, then d1 and d2 are equivalent if and only if for each x belongs to X and each open ball BDI XR in XDI, where R is greater than 0, there exists some S greater than 0 such that BDJXS is contained in BDI XR. Okay, I'll explain this for ij equals to 1, 2 and I not equals to j, right? So this is necessary and sufficient condition for equivalent metric spaces. So this says, suppose X is a non-empty set, right? Then they will be equivalent if for suppose X belongs to X and let B, this is BD1 XR, right? So this is suppose a ball with respect to D1 centered at X with radius R, right? Then it says there has to be some S, there exists, it says what? There exists some S such that if BD1 is a ball, then BD2XS is contained in this BD1, right? So if this is a open ball with respect to centered at X, then there has to be some BD1 here. This has to be some BD2XS. So there must exist some S for which this open ball with respect to metric D2 is totally contained in this BD1, right? And vice versa. So suppose this is X and this one is BD2XR, right? Then there will be some S for which this is BD1XR XS is totally contained in BD2XR, right? So if we choose a ball with respect to one metric, then there has to be one ball with respect to the other metric which is totally contained in that ball, right? then we'll say that these two matrices are equivalent. Okay, so let's keep the proof of this. You can check any book for this proof. Okay, and there is another theorem. This is theorem 1 and theorem 2. Okay, so theorem 2 says this is not necessary sufficient, this is only necessary condition for equivalent. So two matrix D1 and D2 on a non-empty set X are equivalent if there exist real numbers R is greater than 0 such that R d1 xy is less equals to d2 xy and less equals to s d1 xy for all xy belongs to x, right? If this d1 d2 satisfies this condition, then they are equivalent. Okay, but the converse is not true. For the converse part, I will give an example, and I am skipping the proof due to time. Okay, the proof is short. Okay, I will prove this one. So for this proof, I will use this theorem 1. That is, we'll take a ball and we'll show that the ball with respect to another metric is contained in that ball. Okay, so we have to show these two are equivalent. So let x belongs to x, right? And b d1 xt be an open ball in x d1, right? So I have taken a ball with respect to d1. Now we have to find some ball b d2 xs which is contained in this one. Okay, so by our hypothesis, so d1 xy is less equals to r1 d2 xy, right? By assumption, where this r1 is nothing but 1 by r. Okay, so this is for all y in x I have chosen, and for all y this occurs. Now take p equals to t by r1, right? Then I am claiming that the claim is b d2 xp is contained in b d1 xt, right? That I will show. So let y belongs to b d2 xp. This means what? This means d2 xy is less than p, and what is p? P is t by r1, right? T by r1. So r1 d2 xy is less than t, and what is r1 d2 xy? r1 d2 xy is greater than d1. So this implies what? This implies d1 xy is less equals to r1 d2 xy is less than t, right? So d1 xy less than t means y belongs to b d1 x t, right? So this implies this occurs. Our claim is true. So our claim was this. So it is true. So for d1 we have taken a ball and we have found another ball with respect to the other metric which is totally contained in this one. And similarly, if we interchange, then we will see the other case, right? So similarly we can find, we'll see that b d1 x some s will be contained in b d2 xt. Okay, so this means this d1 and d2 are equivalent. Okay, this implies d1 and d2 are equivalent. Right, now we will see that this converse of this theorem is not true. That is, we will give an example where d1 and d2 are equivalent, but this does not satisfy this condition, this one. Okay, so for the converse part we will take this problem. Let xt be a metric. Metric space. Okay, now define d1 xy to be dxy by 1 plus dxy, and d2 xy is minimum of 1 and dxy. Okay, so first check that these two are metrics. These two satisfies the property of metric. Okay, so if you have any doubt, then you can ask me in the next class. So first check d1 d2 are metric. Okay, this means this satisfies all the four properties. So now we will show that d1 and d2 are equivalent, right? So first we will show d1 and d are equivalent, right? Then we will show that d2 and d are equivalent. So this means d1 d and d2 all are equivalent. Okay, so take this function fx equals to x by 1 plus x, which is defined from -1 infinity to r. Okay, so this f is strictly increasing. For x greater equals to 0. Okay, so since this is strictly increasing, and then dxy less than r will imply dxy by 1 plus dxy is less than r by 1 plus r, right? Using the strict this is strictly increasing, that's why this is true, and it is vice versa also. Okay, now this means what? This means this is d1, so this means b d1 x r by 1 plus r is BD of XR, right? Because dxy by 1 plus dxy is d1xy, right? So the ball centered at x with radius r by 1 plus r is nothing but BDXR, right? So it is clear. So this means what? This means so first we have chosen this D, and we found that this BD, this means BD, B, BD1 XR by 1 plus R is contained in B. This is same thing, BDXR, right? So one part is clear. So if we take any ball with respect to the metric D with centered x and radius r, we found this S which is contained in BDXR, where S equals to r by 1 plus r, right? Now we have to show that if BD1XR is a ball, then we have to find some S, right? Now from this, from here, we can also say that BD1XS is equals to BD of X S by 1 minus S, right? Because S is R by 1 plus R, so R will be S by 1 minus S, right? So this is same, these two equation, these two lines. So this means what? This means BD. Now see, this holds only for 0 less than S less than 1, because if S is greater or equals to 1, then the whole set will be X. Okay. Because whenever S is what? S is R by 1 minus R, means it is always bounded by 1. So this line is true, BD1 S XS equals to BDX by S by 1 minus S. It is only for S from 0 to 1. Now when S is greater than 1, means it contains all the values. So it is the whole set X. So this also implies what? So if you are taking BD1, then this implies BD XS by 1 minus S is contained in BD1 XS, right? So from these two, this one and this one, we can say that this D1 and D are equivalent, right? So D1 and D are equivalent. Now we'll show that D2 and D are equivalent. Okay, so to show D2 and D are equivalent, so first of all, D2xy is what? This is minimum of 1 and dxy, right? So it is always less equals to dxy, right? And this means D2xy less than, this implies BD of xy is contained in BD2 of xy, right? The metric, the distance is less than D, D2 is less than D, means the ball BD is contained in BD2, okay, right? Because why? Because if v d2x r the same radius. Why? Because if y belongs to bd xr, then what? Then d of xy is less than r, and by hypothesis we have d2xy is less than equal to dxy, and dxy is less than r, so d2 of xy less than r. So this implies y belongs to b of d2 xr, right? So one part is clear. Now for the another, we have to take bd1 bd and then we have to find a open wall. So take S to be minimum of 1 and r, okay, and suppose bdxr is an open ball in xd, right? Then d2 xy less than s implies what? Implies minimum of 1 dxy is less than minimum of 1 r, right? This means dxy is always less than r. Okay, so this means what? This means y belongs to b d2 xs implies y belongs to bd xr. Okay, so this implies bd2 xs is contained in bd of xr, right? This one. So we have found from these two we can conclude that d2 and d are equivalent. So d2 and d are equivalent, right? So d1 d and d2 all are equivalent. Now we will see that theorem 2, converse of theorem 2 will not be true. Okay, so see that converse of theorem 2 is not true. So d1 or d1 was what? d1 was this one, right? So d1 is always less equals to dxy, right? d1 xy is what? dxy by 1 plus d of xy, right? So d1 xy is less equals to dxy. Okay, now the question is, does there exist some k greater than 0 such that dxy is less equals to k of d1 xy, right? This is the question. This is true. This is the question. Now suppose it happens. So suppose this is true. Then what? Then dxy will be less equals to k and d1 is d of xy by 1 plus dxy, right? Now if x not equals to y, then we can write 1 less equals to k by 1 plus dxy, which implies dxy is less equals to k minus 1, right? So this we are getting if this is true. So this means what? And this is true for all xy belongs to x. So this means the metric space is bounded because the distance between any 2 points is bounded by k minus 1, right? So this means x is bounded, but this may not be true in general. For general metric space we cannot say that the metric is bounded, right? So this is not true in general. True in general because take the Euclidean metric space in R, right? So the distance between any 2 points can be anything, it goes to infinity, right? So that metric space is not bounded, right? So the converse is false, so it is not true. So here we see that this in this problem, this d1 is equivalent to d, and we see that this d1 is what? D1xy is less equals to dxy by 1 plus dxy, right? Now this is less equals to 1, right? So d1 is always bounded, but d can be anything. D is a arbitrary metric space and d1 is a bounded metric space, right? So a metric space, any metric space xt is always equivalent to a bounded metric space, right? This is the importance of this metric d1, right? So every metric space, this means every metric space d of every metric d of a metric space xt is equivalent to a bounded metric. On X, right? So this means the topology is same for D and D1, but it does not determine the boundedness of this metric space, right? So this means this implies the collection of that that what I said means the collection of the open set, that is the topology of the two metric space is same, but it cannot determine the boundedness of a set or the whole space, right? So okay, now I have discussed about equivalent metric space. Okay, and then there is continuity. Now I'll discuss about continuity. Okay, continuity between two metric spaces. Okay, in real analysis we have seen continuous functions from R to R, right? Here the spaces are xt1 and xt2. So suppose let's xt1 and yd2 are two metric spaces. Right, and this function f is from xt1 2 y d2, right? So in the domain we are taking the distance with respect to d1, and in the image domain we are seeing the distance with respect to d2, right? So suppose this is x, and this is y, right? X with d1 metric and y with d2 metric, right? And f is a mapping. Now we say that f is continuous, so f is said to be continuous at some point a belongs to x if the definition is same from the real analysis, okay? If given epsilon greater than 0, then there exists delta greater than 0 such that whenever d1, the distance here is our a, okay, and the image of a is f, right? So it says whenever distance between a and x is less than delta, it will imply the distance between fa and fx will be less than epsilon, right? This means what? This is nothing but, so distance between d1 ax less than delta means x belongs to b d1 a delta implies fx belongs to b d2 fa epsilon, right? Whenever x belongs to this ball, this fx belongs to b d2 this ball. So this is nothing but what? This is f of b d1 a delta is contained in b d2 fa epsilon, right? Right, this is true. So now if we draw in the figure, we see that, so this means b d1 a delta means this one, this is, suppose this is b d1 a delta, right? And x belong, this is radius delta, x belongs to this ball, and then fx, the image will be in this ball. This is b d2 fa epsilon, right? So whenever x belongs to this ball, x is somewhere here, right? This point is x, then fx will be here, right? And what this last line means, what this last line means, this image of b d1 a delta will be contained here, right? This portion is the image of f of b d1 a delta, right? So the image of this ball will be contained in b d2 fa epsilon, right? So first epsilon is given and we have to find the delta which satisfies this condition. Then we'll say that f is continuous at the point a. Now if f is continuous on the whole set A, then we'll say that f is continuous on the set A, right? And for the examples, the trivial example is the constant mapping. right? Example 1 is the constant map. So fx is a for all x belongs to x, right? So it is constant, so it will be continuous. And let's take, and for the second one we'll see that every function from a discrete metric space, every function from a discrete metric space xd to any other metric, to any metric space yd2 is continuous. Why? So f is from x d1 to y d2, right? And this d1 is discrete. Okay, then f will always be continuous. So by epsilon delta definition, so first I will prove by epsilon delta definition. So epsilon greater than 0 is given. Okay, we have to find some delta. So choose delta half. You can choose delta any number which is less than 1. Okay, not half, you can choose any number which is less than the number 1. So then what about bd1 x delta, and x belongs to x. Okay, so bd1 x delta is what? Since this is discrete metric, bd1 x delta will be only x, right? So f of bd1 x delta is nothing but only fx, right? And fx is always contained in bd2 fx epsilon, right? The ball with respect to d2, the ball centered at fx with radius epsilon. The ball always contains the center fx, right? So fx is always contained in that ball. So this satisfies this property, this one, this property. So this means f is continuous at x, and since x is arbitrary point from capital X, so f is continuous on the whole space x, right? So this means f is continuous on x, right? Now we can also show this continuity by the definition from open set, right? From the characterization, if f is continuous, then if and only if u is open in y, then f inverse u is also open, right? This is a characterization. Okay, I'll write that. So position of continuity. So f is continuous if and only if, so f is a mapping from x d1 to y d2, okay, y d2. So f is continuous if and only if u open in y implies f inverse u is open in x, right? The inverse of an open set will be open, and this is same for closed set. also necessary and sufficient. And the second one is the sequential criteria, which is f is continuous on x if and only if the sequence xn converging to x implies f of xn or f of xn converges to fx. Okay, this is the sequential criteria. Xn converges to and only xn converges to x implies f of xn converges to fx, right? So by the first criteria for this two discrete metric, we see that every function from discrete metric space is continuous. Why? So if, right, where d1 is discrete metric. Okay, now we have seen that all the any subset of a discrete metric space is open, right? So if we take any open set from Y, so let U be open in Y, right? So if F inverse U is open in X, then we can say that F is continuous, right? Now here F inverse U is a subset of a discrete metric space. Metric space XD1, right? And we have already seen somewhere, I think, here. So we have seen that any subset, each subset of a discrete metric space is open, right? So if you take any open set in Y, then F inverse U is going to be open. So that's why F is continuous. So this implies F is continuous, right? Okay, I'll stop here, and it is already time. So if you have any doubt in this session, then you can ask me. Shraddha, Amandeep, if you have any doubt, you can ask. Okay, so I guess we don't have any doubts. So okay, so I'll see you in the next tutorial, right? Okay, I am ending this session.